Hello everybody, this is Miss Ross. We are today starting out with Unit 3, covering Day 1 on parallel lines and planes. And we're going to be pretty definition intensive at the beginning here. So some of these concepts you might already be familiar with, but we're just going to provide a formal definition. So first one here to discuss, let me change my pen, is a parallel line. So two parallel lines are defined as two lines in the same plane. So in the same plane that are equidistant from one another. And that meaning each one of their points is equally far apart from a corresponding point on the other line. Equidistant from each other. And never meet. So as we can see in the diagram here, we do have these two lines that are considered parallel, each corresponding point. So if I were to pick a point here and the corresponding point here, they're equally far apart from one another. And notice that regardless of how far we carry out these lines, they will never cross or they will never meet. So that's the definition of a parallel line. Parallel planes, in a similar vein, are planes where each corresponding point is also equidistant, but more concisely, planes that never meet or never touch or never cross, whatever synonym you'd like to use on that. So in our diagram, these two highlighted planes are classified as parallel because if we were to extend them out in all directions, they'll still never cross. So there's going to be no point of intersection. Perpendicular lines, this is also a concept that you're likely familiar with, but we see that these are lines that are right angles, that they intersect at right angles to one another. So lines which intersect at right angles. And remember, we've defined right angles to be 90 degrees. So this would be a 90-degree intersection. So just as we see in the diagram, we usually indicate a little right angle with a box that shows that that's 90 degrees. And remember, just by the nature of how they're interacting, we would create 4 other 90-degree angles as well. Skew lines, this is likely a concept that you've not yet become acquainted with, but these are lines which have no intersection. So which have no point of intersection, but they're not parallel. So, but are not parallel. So if we look at the diagram here, notice I have this line here, and it's not going to intersect with this line. They're actually in different planes. So this is how that happens, is they are located in different planes. Right? So if they are located in different planes, they will never intersect if they are skewed to one another. Okay, so this is kind of a special topic. Again, they never intersect, but yet they're not parallel. So now we're going to look at a few scenarios where we're going to write the relationship between lines AB and CD. So if I go and highlight, here's line AB, comparing this to, let's change colors here, to line CD. These two lines, notice that we have this little box here. So if they're intersecting at a right angle, these would be perpendicular. So we're just classifying based on how they relate to one another. My next scenario, if I'm comparing line AB with line CD here, they notice that these are lines in different planes. And so if they're not parallel, and they're in different planes, that means they'll never cross, they'll never intersect. So these are skew lines. And then finally, we have our last scenario, line AB in yellow here, and we're comparing this to line CD in teal. These lines never cross. If you were to carry them out, they're never going to cross or meet or intersect. So they are considered parallel, and they're equally far apart, every corresponding set of points. So just a little practice with classification. So now let's look at a more complex diagram here and start to pick apart some details. So we're being asked to find all of the planes that are parallel to line SKLM. So let's go ahead and highlight this guy. So SKLM would be the kind of the roof, so to speak, of this diagram. So if I'm looking to find all of the planes that are parallel to this one, meaning they are equally far apart and they would never cross, there's actually only one in this diagram. Let's use a different color to indicate that it would be this guy down below, right? Kind of the ceiling, so to speak, or the floor. The floor and the ceiling are going to be parallel to one another. So we can go ahead and say that plane NTRQ is parallel to line, or to plane SKLM. Next, we're being asked to find all segments that intersect with segment MT. So if I highlight that line segment MT, this guy here, we're looking to find all of the line segments that intersect. So that means that they have to be kind of merging with this line segment. So let's go ahead and highlight all of those. So I'd have this guy here, ML, TR, and then if we think of going back in the other direction, TN. So we can specify that TN intersects with MT. I have ML intersecting with MT, and I have TR intersecting with MT. Let's see, I think we missed even the top one because we actually have two endpoints and they each have two jutting out of them. So this guy as well, MS. So segment MS. And that would wrap up all of the points that are intersecting, or the line segments that are intersecting. The next one has us finding all of the segments that are parallel to line segment MT. So let's highlight this again. We're looking for all of the line segments that are parallel, meaning if we were to carry them out, they are never going to cross or meet or intersect. So we have this guy here. And that looks like that's about it, right? All the other ones would be kind of at odds. They're not going to have that same relationship. So this would just be line segment SN, which is parallel. The next one's asking me to find all segments that are skewed to MT. So we can keep MT highlighted in yellow. And we're looking for all of the line segments that are skew. And remember, skew means in a different plane. They're not parallel and they'll never intersect. So different plane. This one would not work because that's in the same plane, although it looks like it would be skew. This guy though, KQ, so let's say line segment KQ is skew. Q is skew. And then we have, let's see, this one down here is also skew, right? It's in a different plane, never crossing. So NQ, NQ. And we have another, even QR, right? Different plane, not parallel. So line segment QR. And then any other one that we might, let's see, this one even, up at the top, K to L, right, is also skew because it's not intersecting and it's in a different plane. And we also have, let's see, I think that would wrap it up. This guy would be intersecting. This guy would be intersecting. This one's intersecting. This one's intersecting. This one, oh, did we miss LR, huh? LR, oh no, we already established that one is is in the same plane, so that one would not work. So sometimes there's a process of elimination. Oh, when we missed SK here. Or KS, right? That's in a different plane. It's not parallel. So line segment SK. For number 5, it's asking me to find all planes that are parallel to MTRL. So let's kind of backtrack here. So MTRL would be this plane here. So if I'm looking for all planes that are parallel, meaning they would never intersect, would be this guy over here. If I were to color it, it's kind of the corresponding side. So there's just one plane that's parallel. And we can go ahead and name it by the points. Plane S, K, N, Q. Okay, so that wraps up kind of pulling out details. Notice that it is just kind of attention to detail and thoroughly going through and reviewing all of the options. Okay, so now we have kind of a real world application. We have a street map of streets close to Reno High. So we want to, first of all, for part 8, identify a street that intersects with California Avenue. So if I were to highlight California Avenue, you have to kind of know your geography to find this, huh? So here's California Avenue here. Okay, so a street that intersects with California Avenue, we could say Forest Street, we could say Plumas Street, Humboldt Street, Lander Street, Arlington, Gordon, Nixon. Any of those would be intersecting with California Avenue. If I'm being asked to name 3 streets that are parallel, right? So that means if I were to highlight something on the map here, streets that are parallel, gosh, with how I've drawn it here, it's not going to be as evident because they all look like they're the slightest avenue or the slightest angle that's not making it parallel to California Avenue. But if we were to kind of extend this over here, maybe it just makes it more evident that this street would be parallel. State Street, 2nd Street. What do we have over here? 5th Street, right? 6th Street. They're more or less parallel, even though maps are not perfect. So you're kind of improvising a little bit in your interpretation. Asking if streets can be skew. Remember, skew is saying that they are at different planes. They're in entirely different planes and they're not parallel. So there's no way that 2 streets can be skew because all of my streets are hopefully in the same plane, in the world that we live in anyway. So we would say no. All streets would be in the same plane, so they can't be skew. That's kind of our conclusion there. Can't be skew, because if they're all in the same plane, then they already are defying the definition right there. Okay, and then lastly, D is asking for us to name a business or park that could be considered a plane. So we could just say like Wingfield Park. If we were to kind of create a little region that circulates Wingfield Park, that could be considered a plane, right? There's a series of points. Or even if we put, let's see, what's another one? Museum of Art, right? Could be considered a plane, just the space that it takes up. So it's just kind of cool to apply some concepts to the real world.